Hello, AP Calculus. This is Mr. Fugay, and what we're going to talk about today is our last technique of integration, which we're going to call improper integrals. And this is going to introduce a type of integral that we've not encountered to this point. Up to this point in this class, what we've been looking for, and the only integrals that we've been working with, are functions that are continuous and are on closed intervals. So quite simply, I give you a defined start point, a defined end point, and we find the area under the curve of a particular function that has no discontinuities or any issues along that interval. What we're going to run into today is we're going to look at situations where we can find integrals for functions where the functions or the limits are infinite. And we're going to call these improper integrals. And so just a quick visual of what that looks like. If I had this function right here, f of x, and what I wanted to do was I wanted to find the area of the curve from a all the way to infinity, all of the way to an infinite answer, what would this area be right here? And one of the big questions that we're going to talk about here is, would that result in an actual finite answer? And the answer to that is sometimes, as you're going to see today. The other type that we have is, what if in the middle of a closed interval, or what we presumed to be a closed interval, that there was a discontinuity. So let's say I wanted to integrate from A to B, and I wanted to find the area between, but in between there is a vertical asymptote or some sort of a discontinuity standing in my way. What's going to happen to that area? Will it be finite? Will it be infinite? And some terminology that we're going to use to help distinguish between the two is the words converge and diverge. And these are really going to be important words as we especially dive into our series unit, which is our upcoming unit and last major topic for the BC exam. Converge is the terminology we're going to use when a definite integral results in a finite solution. Every single integral that we've done up to this point has been converging. We take the definite integral, we run through the fundamental theorem of calculus and whatnot, and we get a numerical solution. However, when a definite integral results in an answer of either plus or minus infinity, meaning its area is infinite, we're going to say that this integral is going to diverge. So we're going to be using that terminology in today's video. Okay, so let's take a look. There are two different types, as I mentioned to you before. What if there was an infinite limit of integration like there was here on this left-handed example? Or what if there was a discontinuity in the middle of the interval? And that's what we're going to look at here today. So improper integral type 1, an infinite integration limit. So here's three different cases, and we're going to go through a couple of them here in the video. If you have an upper or lower limit of integration that is infinite, what you are going to do is you're going to transform that and basically put a variable in its place. In this case, we're using the letter b. We're going to replace it with a b, and what we're going to do is, instead of writing that as infinity, we're going to take its limit instead, because infinity is not an actual value. What we can do is we can approach it. We cannot actually equal it, and that's really important to know. So we're going to replace it with a b, and then we're going to rewrite it as a limit. And then essentially, you're evaluating the integral as normal. Nothing really changes at that point other than the evaluation. You're going to do that when you have it in the bottom, and in some cases, if you had both top and bottom as infinity, we're going to deal with the same issue. So let's take a look. We're going to go through two examples of this first type. So here's our first integral, 1 to infinity of 1 over x dx. What we want to do is, here's the quick visual, okay? Here's the function 1 over x. We want to start it at 1 here, and we want to go all the way to infinity to see if we're going to get an infinite solution, which will be diverging, or if we get a finite answer. The first thing you're going to want to do is we want to replace that infinity with some sort of a variable, like a dummy variable that's eventually going to get substituted back out. Maybe we'll use the letter b like they did in the notes. So we'll say the limit as b approaches infinity of 1 over x dx. You know it's important for have notation here. We're not going to ever plug infinity in. We're going to approach it. So we're going to continue to write that limit notation. So we're going to still write limit as b approaches infinity, but now I'm going to go ahead and take its antiderivative, which we know that to be natural log of x. We'll need to evaluate this from 1 to b, and that's exactly what I'm going to do next. So we'll plug that in. Again, still writing the limit as b approaches infinity. It's going to be the natural log of b minus the natural log of 1. Now I know when I plug in natural log of infinity, that answer, keep in mind what the graph of natural log looks like, while it looks like it plateaus and has a horizontal asymptote, the natural log function does indeed approach infinity when x is approaching infinity. It approaches a slow infinity, it grows at a slower rate, but nonetheless, this answer is indeed going to approach infinity, as we're going to end up getting an infinite answer minus 0 here, and that's just going to result in infinity. That means the area under this curve right here is infinite, and so our conclusion that we want to write here is that 1 over infinity, 1 over x dx, diverges. That's what our conclusion, our final solution needs to be for this, is that it's going to diverge. Let's look at another example. And so in this case, we're going to look at from negative infinity to negative 2. Let's go ahead and let's write this out in limit notation. And then we're going to go ahead and do what we just did last time, and we're going to take its antiderivative. So we're going to continue to write that limit notation. B approaches negative infinity of negative 1 over x. Evaluate that from b to negative 2. Again, continuing, really you're going through the exact same process of the fundamental theorem of calculus once you've done that initial substitution, and you just have to continue to write limit as b approaches whatever. So when I plug in negative 2, the upper limit is going to be 1/2. I'm going to subtract, and then my lower limit of integration is going to be 1 over b. Now what's this going to result in? Well, when I plug in negative infinity, the 1/2 stays 1/2. When I plug infinity into here, I'm going to get 1 over a very large number, which means it's going to result in a 0. 1 over large results in 0, which means I actually, in this case, get an answer of 1/2. So this answer, our final answer for this, will be from negative infinity to negative 2 of 1 over x squared dx. And what we're going to say is it converges, and we're going to tell ourselves where it actually converges at. So it converges at 1/2, and that's going to be my final solution. And one thought I want you to ponder as you look at these first two examples is 1 over x and 1 over x squared actually are very similar looking functions. They're functions that have asymptotes at 0, x equals 0 that is. 1 over x squared looks like this, and basically what we're saying is from here all the way to infinity, the infinite integral is actually going to result in a finite answer of 1/2. That's a pretty deep thought and something I want you to think about, especially as we move into our next unit on series. Why did 1 over x dx diverge and get an infinite answer, while 1 over x squared converges and it converges at a specific value 1/2? That's going to be questions that I want you to ponder as we move on into the next unit. Now, I put down in the bottom of this video and also on Canvas an example where you want to see where its lower and upper bounds is negative infinity and positive infinity. Here's a YouTube video from Khan Academy, and again, you can check that link out at the bottom of this page or on Canvas to watch that. What we're going to do for the remainder of this video is we're going to look at the second type of improper integral, and that is an infinite discontinuity. What this means is that if f is continuous and has an infinite discontinuity at either one of the endpoints or inside of the interval, that we are going to rewrite that. And again, just like we did with the infinity upper and lower limits, we're going to substitute it out, put a variable in its place, and then perform the integral as usual. So I'm going to do an example where one of the endpoints is is a discontinuity, and then I'm going to do one where we have it in the middle of the interval. Okay, so there's the notation that we're going to use for this. Notice we're going to substitute it out, and the key here is we're actually going to use a one-handed or one-sided limit for this. So let's take a look at our first example for this second type. 2 to 5 of 3 over x squared, and the thing we need to point out here is that at x equals 2 is a discontinuity. Okay, so what that means is I need to substitute that 2 out, and I need to write that as a limit. So I'm going to substitute it out. We'll use the letter b again. Okay, b approaches 2. Now we're going to be approaching it from the positive side because we're going between 2 and 5 when we do this. So it's going to be b to 5 of 3 over x minus 2 dx. And so again, the best part about this is once this is rewritten, you're just going to go through the fundamental theorem of calculus as you would normally do, and then you would evaluate this limit as your final step. So the antiderivative would be 3 natural log of x minus 2 evaluated at b and 5. So we're going to go ahead and do that. So again, make sure you write limit as b approaches 2 from the positive side. We have to write that. I know it might be a little tedious at times to continually have to write that over and over again, but remember that notation is really important in this. And so what are we going to get here? I'm not going to write it equals yet because we don't know if this is actually going to converge yet. So when I plug in my 2 here from the positive side, so this isn't going to change, so it's 3ln3 minus 3ln. Now what's going to happen here is when I plug in a number like 2.01, okay, let's think about it from the positive side, 2.01 minus 2 is going to be 0.01. So this is going to be a number that's really close to approaching 0 from the positive side. What we know about the natural log function by looking at its graph is that there is a vertical asymptote at x equals 0, which means coming from the right-hand side, the natural log function is going to approach negative infinity. So because of that, this is not going to actually approach a specific value. It's instead going to approach infinity. Why infinity and not negative? Because it was already being subtracted. So minus a negative infinity makes it positive infinity. Regardless, that actually doesn't change our answer. What we're going to state as our conclusion is that the integral from 2 to 5 of 3 over x minus 2 dx is going to diverge here. Okay, so this integral is going to diverge. It does not have a finite area between 2 and 5. Our final example today is going to look at where we have a discontinuity in the middle of the interval. Looking at the function 1 over the cube root of x, you might notice that x equals 0 will yield a discontinuity. And so because of that, what I'm going to have to do here is I'm going to have to separate this out into 2 separate integrals, basically exposing that discontinuity as a limit of integration. So I'm going to go from -1 to 0 of, and I'm actually going to rewrite this as x to the -1/3. And then my second integral, which I'm going to write in blue, is going to start at 0, the place where I left off, and it's going to go to 3 of x to the -1/3 dx. And I forgot the dx on the red function. So as we do that, let's go ahead and rewrite it with the limit notation included. So it's going to be the limit as, and I'm going to use the letter a this time. It doesn't matter what letters you use, honestly, but I like to use a's and b's and things like that. Okay, there's our first one. And then our second one, we'll write plus limit, and I'll use the letter b for this one. 0 from the positive side, b to 3, x to the -1/3 dx. Now I'm going to have you pause this video right now, and I'm going to have you complete both of these integrals. What my recommendation is to do one at a time, because if one of these two diverges, it will automatically diverge. As soon as you get an infinite answer, everything just blows up to infinity. So try the one on the left first. Once you get an answer, or if you get an answer, proceed to the one on the right, and then press play, and we'll go over it together. Okay, welcome back. And as it turns out, when you went through this is going to end up converging, so it didn't matter whether you did one at a time or not. But again, if one diverges, they both are going to diverge. So I went ahead with the red function, performed my antiderivative, upper limit, lower limit, and we got an answer of -3/2. So from between -1 and 0, we did get an answer, a finite -3/2. And then from 0 to 3, I went ahead and evaluated its antiderivative, plugged it in. We got a little bit of a nasty answer for this, but 3 cube root of 9 over 2 is a perfectly valid answer, especially if you're on a free response test. You can leave it that way. Since they both had a common denominator of 2, I went ahead and wrote it as a unified answer. You could have obviously left this as -3/2 plus and then 3 cube root 9 over 2, but I went ahead and wrote this out. This will converge here. And this will conclude improper integrals. Please take a look for other practice assignments to work on this, and good luck.